Start here. So we learned about, we've been talking about Laplace transforms in chapter 7. And we've learned some rules for Laplace transforms. We learned how to take the Laplace transform of a derivative and a second derivative and so forth. And then we also, once we have rules for Laplace transforms, we can also then find inverse Laplace transforms. And so we had an example last time where we had a second order differential equation, and we took the Laplace transform of both sides of that second order differential equation, worked out those Laplace transforms, and then we ended up taking the inverse Laplace transform at the end so that we could get the solution to that differential equation. So you have seen now how we can use Laplace transforms to solve a differential equation, and we want to be able to solve a wide variety of differential equations, and to do that we need to learn a few more rules. So this is section 6.3. What you're seeing here, you're seeing a new theorem called the first translation theorem. Okay, and what this says is that if you take the Laplace transform of an e to the at times f of t, so your new function is e to the at times f of t, you're taking the Laplace transform of that function, that's going to equal the Laplace transform of the function f, the little function f of t, at s minus a. Okay, so normally the Laplace transform of a function f of t is just equal to big F of s. Okay, but when you take the Laplace transform of e to the at times that function f of t, the Laplace transform is going to be equal to the Laplace transform for the function f of t, except it's going to be at s minus a. And the proof is very simple. If you take the Laplace transform of e to the at of f of t, by definition, that equals the integral from 0 to infinity of e to the negative st times e to the at f of t dt. That's just the definition of the Laplace transform. But we can rewrite e to the negative st power times e to the at power as e to the power negative s minus a times t f of t dt. And that would just be then the Laplace transform evaluated at s minus a. Okay, hence we call this the first translation theorem. Okay. So are there any questions on the first translation theorem, on its little proof there? Okay. Pictorially, they have in the book here a nice picture here that talks about this shift on the x-axis. So you see there, the f of s function is your normal Laplace transform, and if you shift the s by the value a, then that pictorially is what you're doing. Okay, that's pictorially what you have. So that being said, sometimes they use the symbolism below, but we're not going to get too heavy into the symbolism. We're just going to get to some examples. So if there are no questions, then let me go ahead and get us to some examples here. All right, so let's see. We want, yeah. Okay, let's take a look at some examples here. Okay, and let me deactivate my email. I don't want that to be distracting us at all. Okay, take a moment to copy this example down. Okay, so what we want to do here is we want to find the Laplace transform of e to the negative 2t power times the cosine of 4t. Okay, and of course, for this, we're going to have to use the first translation theorem, because what are we doing here? We're taking this function here, cosine of 4 of t, which is f of t, and we're multiplying it by this e to the negative 2t. Okay, so that's the Laplace transform of e to the at, where a equals negative 2 times this f of t function. Okay, so let me show you how we do this. Okay, and then of course I always have I always have the Laplace transform table handy. Okay, so the Laplace transform of the cosine of 4t, okay, which is our f of t, that just equals, based on the table, okay, s squared divided by the denominator s squared plus 4 squared. Okay, that's right from the table. That's right from the table here. I'll come back here. Right from the table, this formula here with k equal to 4. Okay, and so this is going to give you then s squared divided by s squared plus 16. Okay, that's your, and I denote that as big F of S. Let's see, Antonio. Let me double check. Antonio's asking about the Laplace transform. I think I do have. Now hold on here. Hold on one moment. One moment. One moment. Maybe I do have an error here. Hold on. Let me go back. Sorry. Let me go back here. Yeah, I think you're right. One moment, class. One moment. Let me take a look here. One moment. That's correct. Thank you, Antonio. Antonio caught an error here. this square should not be here. Okay. Thank you, Antonio. Appreciate it. Okay. And I'll fix that on my notes too. Okay. So now by the first translation theorem, we know that the Laplace transform of e to the at f of t is big F of s minus a. Okay, and so what I'm going to do here is make an adjustment on my Laplace transform. And those squareds aren't there either, so I whited them out. So you see, the regular Laplace transform of the cosine of 4 of t is s over s squared plus 16. Well, by the first translation theorem, the Laplace transform of e to the negative 2t times the cosine of 4t, well, the a, okay, here, is equal to negative 2. A equals negative 2. And so wherever there was an s in the Laplace transform, I replaced the s with an s minus the a, which is s minus the negative 2. See that? And so that's going to give us as the Laplace transform s plus 2 over s plus 2 squared plus 16. Okay, are there any questions on this particular example? All right. Maybe give me a thumbs up if you're good so far, and then we'll move to the next example. Okay, Christopher's good, very good. Kathy is good, excellent. Okay, and on to the next example. Okay, let me give you a moment to copy this one down. Yes, Zachary, that was it for that. Let me see, unless I got. Yep, that was the answer. The Laplace transform was s plus 2 divided by the denominator s plus 2 squared plus 16. That was it. All right, let me give you a moment to copy this down. Okay, so here now we want to do an inverse Laplace transform of an interesting looking function. Okay, an interesting looking function here. So, okay, well, how are we gonna approach this? How are we gonna approach this? So, as always, I'm thinking about my table. You know, yeah, well, Zachary, you're right. We're going to have to do the 2s plus 5 divided by s squared plus 6s plus 34. We're going to have to manipulate that. We're going to have to manipulate that in order to find the inverse Laplace transform. Okay, and I always keep my table in mind. But let me first mention here in our solution that by the first translation theorem, the Laplace transform, as you know, of e to the at times function f of t is equal to big function f at s minus a. Well, okay, what I'm looking for now is I'm looking for the inverse Laplace transform of a big function evaluated at s minus a. Oh, what does that equal? Well, if we take the inverse Laplace transform, if we look here at this equation on the Laplace transform, and then we take the inverse Laplace transform of both sides of that equation. Well, on the left, you have the inverse Laplace transform of a Laplace transform, right? Well, that's just going to give you then the function e to the at times f of t, because the inverse Laplace transform and the Laplace transform are inverse operations. So what you're doing is you're taking the composition of two inverse functions essentially, and that gives you what's inside e to the at times f of t. So this means then that certainly the inverse Laplace transform of this big function f evaluated at s minus a does equal e to the at f of t. So the question is, can I take 2s plus 5 over s squared plus 6s plus 34 and rewrite it as some big function of f at s minus a? That's what we have to do. Okay, so take a moment to get to here. Okay, and if there are any questions, let me know. So, okay, this is really like kind of like solving a little puzzle. Okay, so my attention gets drawn to the s squared plus 6s plus 9. I can write that as s plus 3 quantity squared. And then the 25, I can express that as 5 squared. So it's clear. Oh, well, let me say something else. There's something I left out. So when we started here at s squared plus 6s plus 34, 6s is very important, because if I want to complete the square, I have to take, well, if I want to get a squared term out of the denominator, then I have to write the 34 as 9 plus 25. But why did I choose 9 plus 25? Because s squared plus 6s plus 9, okay, let me hold on here. Yeah, let me make this just a little bigger. Yeah, s squared plus 6s plus 6s plus 9 can be written as s plus 3 quantity squared. So the 6s was like a clue in terms of how I rewrote this inverse Laplace transform. But now that I have a 3 here, I have a 3 on the s plus 3 squared. That tells me that A is, well, and it's s plus 3 squared, s plus 3 quantity squared. So s plus 3 quantity squared can be thought of as s minus a negative 3. And so I identify A as equal to negative 3. And so, okay, A equals negative 3. Now I gotta try to take the numerator. The numerator is 2s plus 5. Well, I'm going to want to write that as 2 times s plus 3. Okay, I can do that, but then I got to subtract a 1. And so I can rewrite this function inside the inverse Laplace transform as the difference of two fractions. Okay, the first fraction is 2 times s plus 3 divided by the denominator s plus 3 squared plus 5 squared. And the second fraction is 1 divided by that same denominator. Are there any questions so far? All right. Matthew's good. All right. And really, I know this takes a little time to get used to. You're probably thinking, oh, you know, what's going on here? But really all you're doing is you're rewriting this inverse Laplace transform so that you're able to identify it. And the s plus 3 here, I mean, the first fraction, that is, I can think of that as some Laplace transform of s minus a negative 3. But the second inverse Laplace transform, because I have a 5 squared here, I'm going to want a 5 up here in the numerator. Well, to get a 5 up here in the numerator, I have to introduce a 1/5 in front of the inverse Laplace transform. And so that means then, that now that I'm at this stage here, I can use the second translation theorem in reverse, and this is going to be my inverse Laplace transform. See, this here is the e to the at power part. Whoops, hold on, let me try that again. Let's just, I'll erase that there. This here is the e to the at part. Okay. Are there any questions? Okay. All right. So Matthew saw it. Michael, maybe go back in, come back in, like relog back in. Yeah. All I'm saying is this here is e to the at. All right. No problem. No problem. This is just e to the at. Thank you, Matthew. And a is equal to -3. Okay, so think on this for a minute. Let me know if, you know, we're going to be doing multiple examples today. And let me know if you have any questions, okay? All right, are we ready to move to the next example? Matthew's good. Okay. And maybe a few more thumbs up if we're good. Okay, I'll pause for a little bit here. I want to make sure everybody's comfortable before I move forward. Christopher's good. Excellent. Once you do enough of these problems, you'll kind of get the feel. You'll get the feel for it. Okay, you'll get the feel. All right. All right. That being said, I want to go back to the ebook for a moment. Now there are actually two translation theorems that that you're going to learn. You learned one translation theorem called the first translation theorem. The second translation theorem involves what's called a unit step function. So let's see here. Let's go back into the ebook. Okay, so I'm just going forward here. Just got to find it. Yeah. So, okay. Hold on, let me just click on this twice. Okay, so they mention that in engineering, one frequently encounters an on or an off function. Well, functions that are either off or on. For example, an external force acting on a mechanical system or a voltage impressed on a circuit can be turned off after a period of time. It's convenient to define a special function, okay, called the Heaviside function or the unit step function that can model a function that's off up to a certain time and then on. So when the function's off, the function has value 0, and when the function's turned on, the step function will have a value of 1. Okay, so this is called the Heaviside function or unit step function. How many maybe have seen this in an engineering class that they've taken? All right, well, that's okay. That's all right. So here's how the unit step function's defined. Okay, so we have this script u function evaluated at time t minus a. And that function will equal 0 if t is between time 0 and a. well, greater than or equal to 0 and less than a. And then the step function will equal 1 when t is greater than or equal to a. Okay, so that's called your unit step function. And they have a picture of the unit step function right here. Okay, so, all right, are there any questions so far? Okay, okay. Well, very good. Well, then let's proceed a little bit further here. So, like, I want to go actually right to the example here. So here they have a piecewise defined function. Okay, I don't want to actually, maybe I can just highlight it in yellow. Okay, so this function equals 20t when t is greater than or equal to 0, less than 5. In other words, the function's on between times 0 and 5, and it takes on the value 20t. And then after t is equal to 5, the function turns off. So this step function, you can express this step function, okay, as 20t. Hold on, I don't want that. Hold on, I don't want that highlighted because I want to. Just sorry, we're going to get it. If I can get it, it's a little bit tricky. There we go. So you can write this function f of t in terms of the unit step function unit t of t minus 5. F of t actually can be expressed as 20t minus 20t times the unit step function at t minus 5. Because when t is between 0 and 5, okay, the function equals 20t. So we want the unit step function to equal 0 when t is between 0 and 5. So, and the unit step function at t minus 5 will equal 0 when t is between 0 and 5. So that gets you f of t equals 20t. But when t is greater than or equal to 5, the unit step function will equal 1. And so when t is greater than or equal to 5, f of t will actually equal 20t minus 20t times 1, which is 0. Okay, so this is an example of how to take a piecewise function, and express it as in terms of a unit step function. And that's going to be important because you'll have some problems where in section 7.3 where you have to, for instance, solve a differential equation and your driving function on the right is a step function, and you have to write it in terms of the Heaviside function. And they actually have a picture below just of what this piecewise function f of t looks like. See how it equals 20t when t is between 0 and 5. So it's a linear function with a slope of 20. And at t equals 5, well, when t equals 5, f of t equals 20t. That's 20 times 5, that's 100. Okay, so it reaches 100 at t equals 5, and then it just turns off when t is greater than or equal to 5, and the function equals 0. Okay, are there any questions on that? All right. Well, then let us proceed on then. Let's proceed on. So naturally, you can probably imagine that the Laplace transform is going to get involved in here with this unit step function somehow, and it does. we get what's called a second translation theorem. If you take the Laplace transform of a function f evaluated at time t minus a, well, we're taking a Laplace transform of a function of t. Oh, what is that function of t? It's f of t minus a times the step function at t minus a. Well, it turns out that the Laplace transform of that is going to equal e to the negative a minus s power times big F of s, which is the Laplace transform of your function f of t. Okay, and they prove this below, that this can be proven without too much difficulty. What they do is they take the integral and they write it as the sum of two integrals. They split the integral up at the value t equals a, because the Heaviside function changes when t equals a. So the Laplace transform, by definition, is this integral from 0 to infinity, but you can write that as the sum of two integrals, one that goes from 0 to a and the other that goes from a to infinity. Well, the Heaviside function equals 0 for the first integral because t is between 0 and a. The Heaviside function equals 1 for the second integral because t is greater than or equal to a. Okay, and so the Laplace transform simply equals the integral from a to infinity of e to the negative st, e to the negative st times f of t minus a dt. Well, what you can do is you can do a substitution. Let in that last integral, let v equal t minus a, then dv equals dt, and you can write the integral as you can write the Laplace transform, or that integral, as the integral from 0 to infinity, because the a becomes 0 because v equals t minus a. Infinity just stays infinity. So you'll have the integral from 0 to infinity of e to the power negative s times v plus a, because t is equal now, since v equals t minus a, t is v plus a, and then f of v dv. Factor out the e to the negative as, that factors out of an integral with respect to v, and you're going to get then e to the negative as times the Laplace transform of f of t, which is e to the negative as times the big f of s, big F function at s. Okay, that's how are there any questions on that little proof? I think it's good you see the proof so you can at least appreciate it. All right, well, if there are no questions, then let's look at an example. Matthew, you read my mind. You read my mind. Let's go ahead and look at an example here. Hold on, let me find it. Yeah, here we go. All right, take a moment to copy this example down. Okay, okay, so let's see here. Now, if we think about this, I mean, this sine of t, here, we really want a function of t minus pi over 2. In that spot. So in other words, where the sine of t is, in order to take the Laplace transform, we need to write the sine of t as some function of t minus pi over 2. Well, if you think about your trig days, your trigonometry days, is the sine of t is the sine of t equal to some function evaluated at t minus pi over 2? That's right. Good, Matthew. The sine of t is equal to the cosine of t minus pi over 2. Now let me justify that for you, okay, on fundamentals here. Okay, so what I have here is a picture. I have a picture on the right here. I have a picture of the sine of t and the cosine of t. And I drew this picture because I just think it's good to understand why things are true. So if we were to take the cosine of t based on this picture here, and we were to shift it pi over 2 units to the right, then just think about taking this cosine of t function here and move it 90 degrees to the right. Okay, and if you, well, I want to be careful how I say that. Take the cosine of t function and shift it pi over 2 units to the right. That new function, that shifted function, would overlap the sine of t function, right? So therefore, shifting the cosine of t pi over 2 units to the right shows that the cosine of t minus pi over 2 is equal to the sine of t. And so I can replace the sine of t with the cosine of t minus pi over 2. And of course, the a would be then, hold on here one moment. Yeah, the a would just be equal to pi over 2. All right, and so that takes care of the Heaviside function to worry about. You know, the e to the minus pi over 2s is the e to the negative a over s part. But then you have the Laplace transform of the f of t. Well, the cosine now is your function. So the Laplace transform of the cosine of 1t is just equal to s divided by s squared plus 1 squared. and that's going to be the Laplace transform. Please let me know if you have any questions. Okay, Matthew's good. Excellent. Okay. A short market. Yes, yes. So maybe, let me just see here. Let me just write something down here. Okay, so the Laplace transform by the second translation theorem the Laplace transform, and maybe, hold on, let me try it this way, one moment. The Laplace transform of f of t minus a times the Heaviside function at t minus a. This is an a here. Hold on, I can make it look a little nicer. Hold on. Okay, one moment. Okay, that's an a. Okay, so this then is equal to e to the negative as power times the Laplace transform. This big FFS, remember, stands for the Laplace transform of your function f of t. So the e to the negative pi over s, okay, hopefully everybody's comfortable with that, why that's there. A is equal to pi over 2. Now, the function that we are going to get the Laplace transform for is going to be a cosine function. Well, the Laplace transform of a cosine function, you know, so that's this part here now, right? That's going to be s divided by s squared plus 1 squared. That's what I was saying. Mark, are you comfortable with that? Are there any questions on that? Excellent, excellent. All right. Christopher's good, okay. All right, well, let's move to the next example. So I want to do a variety of examples with you. When you begin working on the 7.3 assignments, you'll be successful. All right, let's go on. Oh boy, this looks interesting. Okay, let me let you when you see this, what do you think of right away? When you see this inverse Laplace transform, what do you think is going to be involved for this one? Well, I was hoping you'd look at the denominator, but that's all right. Begins with a P. Okay. Buying a lot of vowels here. That's right, Zachary. Partial fraction decomposition. That's right. You know it's going to be involved somehow. Okay. All right. So, of course, in order to take the inverse Laplace transform of this function of s, I'm going to have to rewrite the function of s using partial fraction expansion. But what's new, what's a little bit new about this particular function is that you have what are called repeated factors in the denominator. And I'm not sure you've seen that yet, but it's important. I'm not sure you've seen that in Calculus 2. It might be the first time you're seeing this. How do we do a partial fraction expansion of this particular function here? Let me show you. So we notice that in the denominator, the s occurs twice because of the s squared. Okay, and in the, let me see here, one moment, let me come back here. There's some thing that says assignments that's on the screen. I don't know why that's there. Let me see here. All right, well, there, we'll just work. Oh, you don't see anything, Matthew? Okay, well, that's good, that's good. I will not worry about it then. All right, so thank you. So, okay, in the denominator, we have s squared times the quantity s plus 1 cubed. So that means if we factor out the denominator, we have 5 factors. But the s, well, how do we handle something like how do we handle something like s squared? How do we handle that? Well, we write the s, and then we write the s squared. And we have an a and a b above them both. Now, I know the s squared is a quadratic factor, right? It's a second order polynomial, but you just put a b above it. Okay, you just put a b above it. You don't put an a times s plus c, because well, what I mean by repeated, what I mean by repeated, Zachary, is the s squared can be factored as s times s. The s squared can be factored as s times s. So s is a repeated factor. And so when you have a repeated factor, when you do the partial fraction expansion, you write s and then s squared. And then you put a and b over both. Look at the s plus 1 cubed. No, not the same. Not the same. No, it's different, Antonio. It's different than the last section, because the last section, well, want to be a little bit careful here. It's a little bit different. It's a little bit different. The s plus 1 cubed, s plus 1 cubed. That's s plus 1 times s plus 1 times s plus 1. So that's repeated factor 3 times. So you have c over s plus 1. You would expect that. But then you put d over s plus 1 squared plus e over s plus 1 cubed. Okay, now what would happen is if let's say that you were to have, like for b, let's say you were to have like bs plus c instead of just the b. Well, the b would become 0, and the c would equal a number, like the b would equal a number, possibly. So that's how you deal with this with these repeated factors. And it's something that, boy, you know, in calculus 2, it used to be covered quite heavily. When I was in college, I learned all the different expansions for the different cases. This particular case is probably not normally covered in calculus 2. But if you still have your calculus 2 book, it should be in the appendix. But at any rate, okay, there we go. So, all right, so what I'm going to do is I'm going to multiply both sides of this rational equation by s squared times s plus 3 cubed. And that's going to give me this, then, that's going to give me this equation here. Okay, so again, if I write it out, I tend to like to put it in the recording. I'm multiplying both sides of this rational equation by s squared times s plus 1 cubed. Both sides, of course. Multiply it by both sides by that least common denominator. And so, times there. So what you're left with then is this equation here. 5 coefficients to solve. 5 coefficients to solve. And what I'm going to do now this time is I'm going to pick different values of s. Okay. Okay. Why did I set s equal to 0? So this is a second way of doing we have to figure out what a, b, c, d, and e are. And this is another approach to the partial fractions. I could expand out the right-hand side and then come up with equations by equating coefficients from the left and right-hand sides of that equation. And that's what I've been teaching you. But there's another way to finding the coefficients that sometimes is a little easier. You can pick different values of s and then solve for the different coefficients. So like I think to myself, okay, for the right-hand side here, what's like a nice value of s that would make a lot of those terms on the right-hand side drop out? Well, let s equal 0. If s equals 0, the first term will equal 0 because you have an s in there. The third term will equal 0 because you had an s squared as a factor. The fourth and fifth terms will equal 0. So that means you'll be left with 2 times 0 minus 1 equals b times 0 plus 1 cubed. Like I said, only the second term would be left, and hence b equals -1. Are there any questions on that? Okay, well then let's pick another value of s that might be nice. Well, we have a lot of s plus 1 factors here. What if we were to take s equal to -1? That means then that the only term that would be left would be the last term, right? And so 2 times -1 minus 1 would equal e times -1 squared. That means e equals -3. Okay. And then now I got 2 coefficients pretty easily. Now what I have to do is just pick some other values of s, and I'll come up with a system of equations. So I'm gonna obviously I'm gonna pick nice values of s. So hey, what's an easy value of s? A small easy value. Let s equals 1. If I let s equals 1, then when I substitute that in the equation here, in this equation, when I let s equals 1, I'm going to come up with this equation here. 12 will equal 8a plus 4c plus 2d. Okay. Give you a moment to copy that down. All right. Now, so are there any questions up to here? All right. Now, what I'm going to do is the next page, since we only have 5 minutes left in class, I'm going to show you the next page. It'll be there in the recording for you to look at. But I'm going to show you the next page, and then I'm going to go to the last page where, but I'll circle on the next page what you can still put something in your notes. Okay, so may I go to the next page? Okay, very good, very good. So, okay, we've let s equals 0, we've let s equals -1, we've let s equals 1. We have here, so we have, like, we've solved for b, we've solved for e. I have one equation, 3 variables. How many more to solve for a, c, and d? How many more equations do I need? 2 more. That's right, Zachary. So, okay, I'm going to so just write this in your notes. Let s equals 2. Let s equals 2. Then 42 you'll get the equation 42 equals 54a plus 36c plus 12d. Okay, and all the work is just the same as you've it's similar to what you did previously. Then I'll pick another nice s value. I'll let s equals -2. If I let s equals -2, then when I substitute -2 into the equation, okay, into the equation, okay, and again, you know the equation. If I do that, I'm going to get 6 equals 2a plus 4c minus 4d. Okay, and so I'm going to get a system of equations, and I can use MATLAB. So solving this system, MATLAB is going to yield that a equals 5, c equals -5, and d equals -4. Okay. Okay, and so I think what I'll do, you know, well, are there any questions? Are there any questions about this procedure? Okay, so now that we have A, C, and D, now that we know that, okay, may I go to the next page? Maybe give me a thumbs up if you're good. All right, Antonio, excellent. Excellent, Matthew. Okay, well now then, to finish it up, we rewrite the rational expression 2s minus 1 divided by the denominator s squared plus s plus 1 cubed. We write it then in terms of our partial fraction expansion. A equals 5, B equals negative 1, right? Let me double check that. So beautiful, this stuff, I'm telling you. A equals 5, B equals negative 1. C equals negative 5. D equals negative 4. And E equals negative 3. And this is all in the recording. Okay. And so then the inverse Laplace transform of the difference of these functions is just the difference of the inverse Laplace transforms. And I don't think it's too hard to see then. I don't think it's too hard to see that the final in the answer for the inverse Laplace transform. Hold on. Zachary says, shouldn't all of them be to the power negative 1? Oh, well, so are we good? Are we good here? Are we good here? Now I take the inverse Laplace transforms of 1 over s, that's t to the 0th power. The inverse Laplace transform of 1 over s squared is t to the 1st. No, because Zachary, now we're finding the inverse Laplace transforms. The inverse Laplace transform of 1 over s is just equal to 1. It's t to the 0th power. The inverse Laplace transform of 1 over s squared is t to the 1st power. Okay, that's what we're doing. And then 1 over s plus 1, you know, for the last 3, I hold up a little bit. I rewrite the expressions for the last 3. Oh, I'm sorry. Yeah. Okay, thank you. Good catch. Zachary's saying I should have notation. I should have my inverse Laplace transforms here. Well done, Zachary. Thank you. Thank you for catching that. Very good. Excellent. Excellent. Zachary, that's right. Now you're, thank you, Zachary. Appreciate it. All right. And Christopher likes it too. And so now you just get your inverse Laplace transforms and you're done. Okay. Are there any questions? All right, then I'll stop the recording.